let us understand what is regression. And for this, we will start our conversation with the understanding of the straight line equation. So this is something that goes back to our school days. We discussed about coordinate geometry. So if you all remember, the equation of a straight line goes as y equal to mx plus c. This is how we define the equation of a straight line, y equal to mx plus c. And you can see the screen. This is your x-axis, this is your y-axis, and this is the equation of the straight line. So what are the different components of this straight line equation? When we look at the equation of the straight line, what are the different components we have here? So we have something called m. M is the slope of the line, and c is the y-intercept of the line. These are the two components of the straight line equation. So this is the equation mx plus c, and there are two components. One is the slope of the straight line. Slope is giving us an idea about, like, how much of slope, how much of elevation. Okay, so for every axis, imagine you're climbing up a hill and you look at the slope of a hill. So that is how we visualize the meaning of slope. And mathematically, when we look at a straight line equation, this is how we can think of slope. Okay, so you can see we are traveling from point A to point B. So this is the straight line. So I'm just trying to put some arrows to make it easy to understand. This is the straight line equation. And you're traveling from point A to point B. And as you travel from point A to point B, there are two types of movements that are happening. One is a horizontal movement, and two is a vertical movement, isn't it? So when you climb up a hill, you're traveling in two broad directions. So one, you're traveling horizontally, and two, you're traveling up vertically. And slope is kind of capturing both those variations of movement. So it is giving you delta y by delta x. So change of y. So y final minus y initial divided by the change of x. X final minus x initial. So we look at the change of y and we divide that by the change of x. That's how we find out the meaning of slope. So for every unit distance you travel along the x-axis, how much distance are you rising along the y-axis? So that's how we understand the meaning of slope. So for every unit distance that you're traveling along the x-axis, so x-axis is the horizontal direction that we are traveling, right? So for every unit distance that we are traveling, for every unit distance that we are traveling along the x-axis, how much distance are we traveling along the y-axis? Okay, so if this is a unit distance that we are traveling along the x-axis, how much distance are we traveling along the y-axis? So that's the way how we understand the meaning of slope. And similarly, there is something called a y-intercept. So what is the y-intercept? Y-intercept tells us that this is the point at which the line intersects the y-axis. This is the y-axis, the point in the line intersects the y-axis at this point. So this distance is called the y-intercept. So y-intercept is basically the distance of this point from the origin. It is the point at which the line intersects the y-axis. That is the y, and the distance from the origin is what we call the y-intercept. Now, this equation understanding is important because going forward, we will see that as we get into applications, we will eventually use this equation going forward. Okay. These are a few examples. You can see when the equation is y equal to 2x plus 3, this is how the straight line looks like. So 2 is the slope and 3 is the intercept. And if we have the straight line equation, which is minus 9x plus 7, then the slope is minus 9 and the intercept is plus 7. This is the way, again, how we understand the intuition behind what is the meaning of a slope. Okay, hope everybody is clear, everybody is aligned, and everybody in the audience understands the meaning of a straight line equation. Now, moving on, uh, let us try to correlate this with respect to what we have done so far with respect to supervised learning. Okay, so this is the core of what we discussed in supervised learning. If you all remember, we give the machine lots and lots of input-output combinations, 1, 2, 4, 5, 6, 7. Okay, so let me do one thing. Instead of starting this way, let me start with the whiteboard and let me explain this in the whiteboard. Okay. This is just to explain to all of you the core idea behind what is going on in uh, regression. Let us see. So we have x equal to 1. I'll take lots and lots of these XY combinations. That's the core idea. So we have XY combinations. You can see, all of you can see the screen. X is 1, Y is 2, X is 3, Y is 4, X is 5, Y is 6, and so on and so forth. So these are the input output combinations that we are taking. And now we can visualize this also in a nice way. So whatever I've written here, we can nicely visualize the whole thing. So on the right hand side, I'll draw the regression plot. So this is how the regression plot will look like. So we have x-axis, we have y-axis. I'm sorry, this is the y-axis. So this is x-axis, this is y-axis, and these are our data points. This is 1, 2, this is 3, 4, and this is 5, 6. Okay, so this is pretty much the idea of what we have discussed in supervised learning so far, isn't it? So we are looking at lots and lots of these input-output combinations, or so-called XY combinations, and uh, on the basis of these input-output combinations, we are trying to find a line or plane or mathematical surface that best fits the points. So in a way, we are trying to find out the line of best fit. So what is the best fit line? We are trying to kind of find out the the best fit line. So the best fit is what we are in a way trying to find out. So what is that best fit line? How do we do that? How do we visualize the best fit line? So this is the way how we do this. Okay, so I'll take a scale and try to explain. So this is my 1, 2, this is my 3, 4, this is my 5, 6. So what is the algorithm actually trying to do? What exactly is the algorithm trying to do? This is pretty much what we discussed in the morning part, right? So we talked about the data. This is my data, and we are using some algorithm, and we are building a model, right? So the model part is the end result of what we are getting. So what is this entity doing? How are we learning? What is this fit happening? What is this model dot fit? What is this fit? What is this model training? How is it training? How is it learning the rules? So given this data, we are trying to find out what is the line that best fits the points, right? I know this doesn't look perfect. Let me just try to realign the points a little. Yeah, don't worry. I mean, this is 1, 2 will be somewhere here actually, little raised. 3, 4 will be little raised. Otherwise, actually, my line was passing to the origin, which is not right. Anyway, so now we are trying to find out. There are infinite number of lines we can draw, right? If you look at this 2D, two-dimensional mathematical surface. So in this two-dimensional mathematical surface, there are infinite number of lines we can draw. And out of all these infinite number of lines, we are trying to find out what is that line that best fits the points. That is what we call the regression line. So out of all the infinite number of lines that we can potentially draw in this two-dimensional mathematical space, out of all the infinite number of lines we can draw in the two-dimensional mathematical space, we have the line of best fit. That is what we call the regression line. And you want to know what is the equation of that line? The equation of this line, interestingly, so this is the best fit. The best fit we have got, right, is y equal to x plus 1. Okay, and I think this is based on everything that we saw until now. See, the slope is 1. This is, if you compare this with the template that we talked about, mx plus c. See, the m is 1 and the c is also 1. So the slope is 1 and the intercept is also equal to 1. So that's the overall idea. Okay, so this is the best fit line that we have got. And this is how it relates back to everything that we talked about so far. So we have the data. We are using the regression algorithm. There is some algorithm that is playing out behind the scenes. There's some best fit line that we are trying to draw. And what is the model, what is the rules, or what is the mathematical function that we learn at the end of it all? It is y equal to x plus 1. So we can see it visually and we can also see it mathematically. See, even mathematically, if we try to do this manually, the relationship between x and y is y equal to x plus 1. This is what happens in model training. So when we talk about training a machine learning model, this is effectively what we are doing. We take the data, we try to find out the best fit, we get the equation, and given some new x, given we have some new value of x, we can fit this into the equation. I mean, if I have to do this visually, given I have a new value of x, what I will do, let me erase this part. So given I have a new value of x, let's say x is equal to 9, one, I can substitute this to the equation, and this time I will do a model dot predict, and y is equal to 10. Predicted value of y is 10. Visually, how will I do it? Next time x is equal to 9, you try to extend and you predict, hey, given this is the line, if x is 9, the predicted value of y will be equal to 10. So that's the way how you can visualize what is going on in linear regression. I know there are a lot of questions that people will still have. One very common question that you will have is that is it guaranteed that the line will perfectly pass through all the points? No, it's not guaranteed. I mean, the line is not, it's not guaranteed that the line will perfectly pass through all the points. It's possible that the line, that we are talking about will not pass through all the points. Okay, so that is one thing that everybody will need to keep in mind. Okay, so it is not absolutely guaranteed that whatever best fit line that we have right now, it is not guaranteed that the best fit line will pass through all the points. It is called best fit, but it may not be a perfect fit. So what I mean to say is you can still end up with a scenario like this. You might have a set of data points that are a little bit more distributed a little bit more naturally, and then your best fit line will be somewhat like this. It's a best fit. It's not a perfect fit. It won't pass through all the points, but it is going to pass through most of the points. So that's one of the variations that I want to talk about. The other variation is that the equation need not necessarily be linear. Okay, so whatever equation that we learned here, it doesn't necessarily have to be a linear equation. You can also end up learning a non-linear equation. So we have some data, we use some algorithm, and we can also end up with a non-linear model. Okay, so instead of a line, this is a linear model. We can end up with a non-linear model that passes through all the points. So that's the other aspect that I want to also talk about. Okay, so this is all. This is what initial part is about. So we talked about what is a straight line equation. We talked about how to how to visualize this and how to correlate this idea with everything that we talked about so far. So this is what we discussed, how we find the best fit line, and this is the way we visualize regression. Whatever we'll do in code now over the course of the next 1 hour, this is the way to visualize what is exactly is. This is the best fit case, but it need not be best fit. And the second idea is that it doesn't have to be a single variable. What I explained right now was with respect to a single input or a single feature. Okay, so it is like, let's say we are trying to predict the salary of a person. A very good use case of regression is in the HR department. Let's say you have a new applicant, you have a new uh, employee that you want to hire. The person has gone through on the rounds, interview rounds, and have cleared the interview. And you are going to be offering the person a role in the company. And a good use case would be to predict the salary. This is a very good use case of regression. So how will you do it? What's the idea behind it? So you will look at the historical data in your organization. So it will be somewhat like this. You have the experience, which is the input, and your salary, which is the output. Okay, so you look at the historical data. You look at how people in the company, how much money they typically make. Okay, so you look at the historical data in the company, how much money people in the company typically make. So when somebody's experience is this, their salary is this. When somebody's experience is this, their salary is this. And when somebody's experience is this, their salary is this. So we are looking at the historical data in the organization. We are looking at the patterns. What is the experience? What is the salary? What is the experience? What is the salary? And again, what is the experience? What is the salary? We're looking at the historical data. And based on the historical data, we will use some algorithm and we will build a mathematical model. We will find some relationship between the x and the y. So this is in line with what happens in the company. In the company, you're trying to figure out that, hey, what is the typical pattern? What kind of money do people typically make based on their experience? And you learn the relationship. You learn the some equation between X and Y. Let's say this is the equation that you learn. It's very generic, I know, but let's take an example. So this is the model that you learn based on your data. Now what will happen? Now let's say you will use this model for your future hirings. Okay, so that's machine learning, right? So you take the data, build a model, dot fit model training, you train the model, you learn the rules. And next time a new applicant is to be offered, if the experience of the person is 5 years, so this person has 5 years of work experience, and based on that, you will predict what is the salary. So now what will you do? There are two parts. One is model dot fit, and here it will be model dot predict. Because you already learned the equation, you have the rules, and now that the experience is 5 years, you put 5 here. 5 into 2 is 10 plus 1, 11. So the model will predict 11 salary. So that's the way how the two components are working, fit and predict. Now, very important. Here, I used only the experience to predict the salary. I mean, we are framing it as a very basic problem. We are looking at the experience of the person, and based on the experience of the person, we are trying to predict the salary of the person. Very basic use case. Okay, we are looking at the experience of the person, and based on the experience of the person, we are trying to predict what is the salary of the person. That's the way how we are framing the whole thing right now. But if you look at a real world scenario, the salary of a person actually depends on many other parameters. The salary does not just depend on the experience. The salary of a person depends on multiple other parameters. The salary will depend on your experience. The salary will depend on your, let's say, the interview rounds, how much of marks you scored. Your salary will also depend on your skill set. So maybe if you're applying for an AI team, your salaries scale will be very different. If you're applying for a full stack development team, your salary scale will be very different. So the salary of a person, the output will depend on many other inputs. Even during the model training, while you're framing the problem, this is a very, very important part of ML, where you have to decide, you as a developer, you as a data scientist, you will have to decide that when you want to predict the salary, what are the inputs which you can use to predict the output? What inputs will have the highest relationship with the output? And that is where we will typically do relationship with regression with multiple variables. So the example I showed you here was with a, based on single X, you're trying to predict single Y. It's easy to visualize, but oftentimes we will end up with more complex use cases like this. So the same way that we can have a straight line equation, we can also have a planar equation. So y is a mathematical function of multiple features. You can see m1x1 plus m2x2 plus c. Similarly, you can extend it. m1x1 plus m2x2 plus m3x3 plus 3 plus c. Or m1x1 plus m2x2 plus m3x3 plus m4x4 plus c. You can have the output y, which depends on multiple input x's. So the output depends on multiple input features. That is the idea. And this is what we refer to as multiple linear regression. Okay, and you can see the ideas are very, very similar. The only thing is that instead of a line, so now what we have instead is basically a plane. So that is the only difference that we have here. Instead of a line, we now have a planar equation. Okay. Now let's move on. Let's come back, and this is just one more way to relate to it. This is a little bit more technical in terms of geometric understanding. So if you remember, we talked about slope a while back, and I discussed that slope tells you that for every unit increase in x, what is the change in y? So this is the way you can understand what slope means. What is the meaning of a slope? So for every 1 unit increase in the value of x, what is the change in the value of y? So for every 1 unit increase in the value of x, what is the change in the value of y? That is how we define the meaning of slope. Now, if you relate it to the examples that we did so far, let me take you to this example. Y equal to, excuse me, y equal to 2x plus 3. If you look at this example, imagine this is the example we did with respect to salary and experience. I'll call it salary. So y is the salary and x is the experience, E. What it means is for every 1 unit increase in experience, the salary goes up by 2 units. So this equation that you're seeing on the screen, whatever this final equation that we are learning, so we take the data, use an algorithm, build a model, which is an equation form. That final equation that you end up getting, there is a lot of meaning hidden into that equation. You can really understand in detail what that equation means. So in this case, y is equal to 2x plus 3 means that the slope is 2. And what is the meaning of this 2? What do we mean by this slope 2? Slope 2 means that for every 1 unit increase in experience, the salary goes up by 2 units. So when we look at the entire historical data of all the employees in the company over the last 5, 10 years, this is the pattern that we have discovered. When we do that best fit line, this is the general pattern that we have discovered that usually on an average, see, there will always be outliers, there will always be exceptions, and some people are making a lot of money, some people are maybe, let's say, this whatever reason they've taken from a different sector, domains, career breaks, and maybe they're not on the same pay scale, or their progressions and promotions are due. But if you look at the general average trend in the company, on an average, for every 1 year increase in experience, if you see the line, for every 1 unit that you travel forward, on an average, whichever part of the line you see, from here, whichever part of the line you see, for every 1 unit that you travel ahead, you'll go up 2 units up. That's the idea. Okay, and the same way, what we can do, the same way you can also see a similar pattern with respect to multiple linear regression. This is the thing I wanted to highlight. So this is the equation of a line. Similarly, this is the equation of a plane. There are two variables, right, to predict the output y. And this is the example. You remember salary equal to experience plus marks plus c. And this is the way to interpret this. Okay, this is the way you interpret the meaning of multiple linear regression. If there are multiple inputs which are used to predict the salary, once you get that equation, you get a very nice interpretation of what that equation means. And that is, I would say, one of the most powerful features of linear regression. It is a very basic algorithm. As we go through the topics, we will discuss more advanced algorithms which may not take the shape of a mathematical equation as simple equation that we are seeing here. Uh, but even this very, very simple equation has extremely powerful qualities because it helps us understand what is going on behind the scenes. The interpretability and the explainability is very high. So by looking at this equation, we can say that on an average in the company, keeping other factors constant, if the experience goes up by 1 unit, the salary goes up by 2 units. And keeping every other factor constant, if the experience goes up, if the marks goes up by 1 unit, the salary goes up by 3 units. So this is very interesting, which tells you that the marks has a very, very important role to play on the salary. Even if you get more, let's say it's a very scientifically developed exam. Let's say all the company employees have come together, all the departments have come together and framed the questions as an example. So they have tried to frame the questions in line with the kind of work they do, the use cases they follow, and all that. So they have designed a very exhaustive set of questions, and and they have discovered that over the years, that every 1 unit increase in marks, if some of the candidates are scoring even 1 mark more, that translates to a 3 lakhs increase in salary. And I'm just saying as an example because 1 marks is scaled data. And don't think it's on a scale of 100. So maybe let's say out of a scale of 10, it's scale data that we're taking. Okay, so on a scale of 10, let's say every 1 mark more that you score, the difficulty level as it gets harder and harder, your pay scale on an average goes up. Okay, keeping other factors constant.